Welcome to the presentation considering timing from logical architecture to ECU integration. My name is Alexander Albrecht and I'm working at the German Aerospace Center, and I will present to you the topic with my colleague Raphael Weber from Vector. The German Aerospace Center is a large-scale research facility in Germany which has about 9,000 employees and focuses on areas such as aviation, space, but also transport, energy and security in general. Now, I also want to introduce the importance of timing effects, because timing plays a central role also in the aviation and space industry. And the first effect that I want to introduce is the time delay. And time delays can lead to chain reactions, which you might know from flying or using the train, where a delay in the first flight might also impact the second one. So what we can see here is that isolated timing consideration is not sufficient, and that we need to consider timing as a holistic problem that we need to solve also for our systems and not only on this high-level overview. So the next property or timing effect is time sequencing. And time sequencing is very important. Also, I brought an example from the aviation side, where aircraft, when they take off, also during flight, they produce a wake vortex, as you can see on the right. And if you have a following aircraft that takes off and flies into such a vortex, it is possible that it experiences a different lift on the wings of the aircraft, which might lead to a roll of the aircraft and even potentially an accident. So here, a correct time sequencing of when the aircrafts take off is required, especially for sequences such as a large aircraft starts and then a smaller aircraft follows up. And then we have properties or timing effects such as time synchronization, where a precise timing is very important to calculate things like the GNSS positioning. And here, even effects have to be considered, such as time dilation, to keep the clocks accurate between the satellites and also between the person that is using this information from the satellites on the ground on the Earth. After motivating the topic of timing, I'm going to go into the DLR use case that we use to check the tools and methods that we implemented. And these methods and tools come from the XANDAR project. So we will give a brief overview of the XANDAR project and then also the related timing concepts and tools, and then finish up with the timing application in the DLR use case and a conclusion. For the DLR use case, I'm going to start with timing in general in aviation and avionics. And what we have seen already is that there are many effects to consider, so timing is manifold and also difficult to handle. But at the same time, timing is important for success and has effects on functionality, but also safety and security. And if we take a look at different use cases, we can see for some use cases, timing is maybe not as important in the aviation sector, but for others, such as urban air mobility, which is emerging, it is very important to consider timing because the time to collision is much smaller. And this means that timing in aviation is even increasing in importance, and the same is true for the systems that are on the airplanes, which is the avionic system, so aviation electronic. And aviation electronic is composed out of mainly two parts, the computing units that are integrated into the aircraft, and then also the electronic consumers, which are something like a display system, but also cabin systems or the flight control systems, which are using electrical signals. And for these, timing isolation is something that we use in aviation to make sure that we have deterministic timing. And similarly, we also use time-triggered scheduling, such as TDMS schedule. To then test also the timing concepts that I developed, we also need a use case. And for this, we decided to take a look at a flight assistance system for urban air mobility. And in urban air mobility, there are increasing threats of terrain and traffic. So we need to consider also these topics in our flight assistance system. And these are topics that are already considered for large aircraft, but it's also important to consider the smaller aircraft so that they also have this flight assistance functionality. because there are also a lot of accidents related to these topics. So we have terrain awareness and warning as one of the main functionalities, and then also airborne collision avoidance. And to implement the system, we envision an architecture as shown right here. We have sensor units that are providing information to an avionics computer. And this information is then used to calculate advisories that are shown to the pilot on the aircraft to avoid dangerous situations. And therefore, we can see, for example, here in an example, another aircraft is approaching, and we can identify the increasing threat and provide advisories so that he's able to avoid this dangerous situation. Now, this also concludes the first part, and I want to hand over to my colleague Raphael from Vector so that he can explain the XANDAR project and also the timing concepts and tools.
Okay, thanks, Alex. I will show you now, give you some overview over the XANDAR project and the design flow. So, how can we ensure correct timing? Since we are talking about timing, how can we ensure that actually? So it's possible just to run some test. We build our car, crash it, and see if everything works from the timing perspective, everything is correct, and then we have a test. If the airbag, for example, opens up in the correct time frame, then everything is fine. We can do some more tests, maybe crash 2 cars to be more efficient. Maybe we can more tests, and we can even do that for planes, which might be a little bit more expensive on the long run. So maybe that's not the best way to go to ensure correct timing. So this is why there's the XANDAR project, and the XANDAR project has a specific goal to deliver a mature software toolchain realizing the correct by construction approach. And also specifically here in this case, we consider timing. So from a specification view, we start from timing early on and do all the timing specifications seamlessly on each level of abstraction. The XANDAR project is a 3-year project. It's almost about finished in the end of 2023. And the funding is about 5 million from the EU. And we are a neat little consortium of 8 partners. The XANDAR toolchain, so the tool flow that we considered in the XANDAR project is shown here, and we enriched it with specific points in the tool flow, in the toolchain where we consider timing. So we call these timing stages. And there is the 1, the 2, and the 3. And not to going into much detail here, so we start with a model-based front end. In the architecture modeling, there we have the logical architecture timing and the software architecture timing. That's number 2. And then we go into the back end, and there we have some more details about the timing in stage 3. So to be precise, what we can do in a vector tool, for example, in Prevision, we have this activity modeling possibilities that we do in the architecture modeling. We have logical architecture timing, verification, and validation in Prevision, so on a very high level. We also have that in software. And then in stage number 3, we have software timing verification via some simulation, where we have also some overheads in the timing simulation. Okay, so when you talk about timing, we have to first, of course, take a look at some concepts. So what is timing? And in AUTOSAR, there are a few concepts defined for timing. First of all, it is an event. So AUTOSAR defines timing events, timing description events, because you describe what you would you like to observe. So if, for example, some software component receives a signal, that is an event. If some software component sends a signal, that is an event. An event is just something that has a timestamp, and it marks that something is happening, some state change or some data exchange, for example. And one important property of that is it has to be observable. If the events are not observable, then we cannot talk about, or we cannot give any guarantees about it, because then we never know if they actually happened or not. Then we can connect these events to event chains. and say, okay, we have, for example, 3 events. First, the first event, then a second event, and then the third event. And these 3 events in that order represent a cause-effect chain. So this is very important for the event chains in AutoSAR, that there is a causality from the start to the end of this chain. And of course, it has to be observable. So this is how you can concatenate multiple events into event chains, and you can specify multiple event chains. Then if you want to take a closer look at these event chains, maybe we have at some point have a trace that we would like to analyze, we can formulate some constraints on events and event chains. For example, we would like to say, okay, this event chain with these 3 events may only take a maximum of 2 milliseconds. That could be a requirement, a latency requirement. And in AutoSAR, these constraints have 2 different roles. Can be requirement or a guarantee, where a guarantee is a little bit more strict than a requirement. Okay, so let's take a look at an example. So if we have a black box component which has 2 inputs, so here is one input, the upper and the lower, and there's one output. Where do we see actually some events here? And we can see events here on the input, on the inputs and on the output, and say, okay, let's just create 2 event chains where we just have this first event and the second event, and that's already a chain because it's 2 events. So we have an upper chain and an upper event chain EC1, which has a constraint of 20 milliseconds, and we have a lower event chain with a constraint of 30 milliseconds. So between these 2 events, for example, only 30 milliseconds may pass. If we go now deeper into the decomposition, so if we decompose the black box component, we may have subcomponents. So for example, C1, C2, C3, and C4, and also some signals to be exchanged between the components. And then if we do this refinement, we also see additional new events. So whenever we send a signal and receive a signal, that's a new event because time can pass between these points in time. And then we can also refine our event chain and say, okay, to be more specific and to be more detailed with event chain 1 and event chain 2, we can just say, okay, I give some sub-event chains, EC11, 12, 13, and so on, and also assign specific latency constraints to these segments, to these event chain segments, they are called. And then we have that for EC1 and EC2, and there may be some inconsistency there already, because in some cases, the event chains and the segments talk about the same thing, the same events. For example, the signal 3, so the sending and the receiving here, it's constrained to be 4 milliseconds on the upper event chain, but it's constrained to be 5 milliseconds on the lower event chain. So there might be some differences, which is okay, but maybe that's not intentional. So, and there might even occur some errors in the specification of these event chains. And yeah, for example, what happens if we change this to 4 milliseconds, this upper event chain here, is it still valid? So is event chain 1 still valid? And the answer is no, it's not, because the sum of the segments is bigger than 20 milliseconds in this case. We actually know from the lower event chain that these 3 milliseconds will hold, so we can actually say it's 4 milliseconds, but within the scope of the sum of the event chains, this is an error. And this is one possibility to have already some validation for the consistency of the event chains on the logical architecture and on the software architecture, so stage 1 and 2. And this is just a simple example. Now imagine if we have more components, which may be even more complex. So this is very helpful. If we want to talk about some load estimations, we can also annotate to the components, for example, some activation patterns, a sensor sampling rate, for example, that a sensor is sent with a specific frequency every 20 milliseconds, for example. And then we know, okay, maybe this component one already runs every 20 milliseconds. We can assign budgets to the components. There's a small difference between the latency constraints from the event chains and the segments, because as you can see, there might be different event chain constraints. Here it's 6 milliseconds, here it's 5 milliseconds. But what we actually give to the software developer, the guy who implements that component, may be something different. So for example, we say, okay, he has a budget of 4 milliseconds, not more than that. So there's a design decision to be made about this. And once we have that, so we have all the activation patterns, we have some sampling rates, for example, we can just say, okay, what kind of load that we have here in this system. So if, for example, we have this 2 milliseconds budget for component 1, and we know it runs every 20 milliseconds, we have a load of 10%. And we can sum out all the loads, and then we can initially estimate some load that this whole system would be able to or would possibly require. This is still very abstract, but you can have an initial load estimation here. Okay, how did we actually implement that in Prevision? So we built some XANDAR prototype in Prevision to specify the timing and to model that. So on the right side, we see here a logical architecture excerpt. And on the bottom, we see here the event chains. So these are here, these two lines. Then we refer to these events, something that happens on the port. So the port sends data and the other port receives data. These are our event references. And then we can constrain the events or the latencies between the different events by just annotating this number here. This is a prototype, so this is not part of the product, but this is one way to model event chains and events and constraints on it. And once we have done that, we can just run a timing consistency check and see from the report if there are any errors or warnings or informations. Maybe something is actually really inconsistent, or maybe we have some slack in the event chain specifications that we want to be able to use or to remove. Okay, so this is stage 1 and 2, so logical architecture and software architecture. Then there's a big jump from the software architecture to stage 3, where we also have the operating system, tasks, and all the basic software stuff. This step is more involved than I can actually show here, but rest assured, it is possible to automate that. And we did also show some concept, some prototype about this, but I will not go into detail in here. So there's a way from Prevision to the TA tool suite, and the TA tool suite, that's one tool to run timing simulation. And then we can see here, for example, in the Gantt chart, okay, these are the event chains here, these red lines, and we can also have some load chart and some metrics on the bottom. And we can again have some report generated out of this with a customizable report template. And then we can, for example, see if there are any preemptions in the time-triggered schedule that should not happen because we have fixed time frames, and if some deadlines are missed. So this is all possible to see in the TA tool suite in the report. And now we'll hand back to my colleague Alex.
So now we are going to take a look at the use case application. So first of all, if we want to apply the timing concepts on a model, we need to create a model. And therefore, we have the model-based front end in the XANDAR toolchain, where we use requirements and architecture modeling to generate this model in a systematic fashion. And this works like this. We use the Prevision tooling, as seen on the right, and we start by modeling use cases, activity diagrams, and we derive requirements that we can use to then also set up the logical architecture design. And the logical architecture design is also what we are using for the initial stages of the timing validation. Therefore, I'm going to take a look at the architecture right now. And if we consider what we've said earlier about the use case, we want to provide a system where we have terrain awareness and warning and also collision avoidance as the main functionalities. And to make this happen, we need information about where our own aircraft is and also where the other aircraft are. And this means we need an aircraft state acquisition as well as an intruder localization. And what is interesting here, the aircraft state acquisition is something that we need for both functionalities, for the terrain awareness and warning and also the collision avoidance. But the intruder localization is only used for the collision avoidance. So in addition, we then use the information that is generated in forms of advisories to the pilot. So how he can avoid the dangerous situations. We forward them to the instruments, and then we also can display it to the pilot. And to consider timing, we now also defined event chains and timing constraints. So what we see here is, for example, for the terrain awareness and warning, an event chain where we define that the aircraft state acquisition is only allowed to take about 90 milliseconds. Since we also consider this aircraft state acquisition in the collision avoidance event chain, which is the red one below, we need to consider also the 80 milliseconds as a requirement for this part of the logical architecture. And then we can use the functionality that was implemented to check if our timing requirements are as we expect them to be and that we do not make any mistakes. So let's take a look at what we as specified as an addition. We also specified a timing budget. So we need to define a final time constraint that the developers can use and that specifies a worst case execution time for our component. And then we can use the functionality to validate that this timing budget is also in line with the requirements that we specified in form of event chains. And here we can see different errors pop up if we execute the validation functionality. First of all, we are informed that we have two timing requirements for the same component. So 80 milliseconds from the lower timing event chain and also 90 milliseconds from the upper green event chain. This means that we need to consider the strictest timing requirement, which is 80 milliseconds in this case. And this also brings us to the second error, which is displayed right here, that we have specified a timing budget of 85 milliseconds, even though our strictest timing requirement is 80 milliseconds. So we can also address this error and make sure that we do not have inconsistent specification for our system. The same can be done then also for the software architecture. In the software architecture, we just took the logical architecture, refined it a bit, but we also only look at it from a high-level view. So here we also have the terrain awareness and warning, the collision avoidance, and we now included the aircraft state acquisition and the intruder localization into one pre-processing component and have a post-processing component, which is selecting the final advisory that is displayed to the pilot. And again, we can specify the timing requirements and make sure that we have all specified in a valid way. And this software architecture can then also be exported and used for example, tools like the TA2 suite to even go into further timing considerations. And this also brings us to the stage 3, where we consider the timing of our software architecture, the timing schedule, and also possible errors that we have in the specification. And here we not only consider the components itself, but also aspects such as read and write times. So we have the collision avoidance system. We consider the read time, the execution time, and the write time. And what we can see here is that we have actually a start delay, which is highlighted in gray here, for the execution of the collision avoidance functionality. And this is something that we want to prevent because we want to have a time-triggered schedule without preemptions. And therefore, we are able to identify these issues quickly with our timing validations using the TA2 suite. and we are able to fix these issues then for our final specification, that we can also implement the software correctly. Overall, this helps to prevent issues later in the process, and also makes sure that we do not have to test, as Raphael showed, with the crashing cars. So we make sure that we can catch the timing errors before we actually bring the product out in the streets or in the air. And this also brings us to the conclusion, which is that timing is essential and even increasing in importance, especially in the aviation domain, where we currently see a trend towards more urban air mobility, where the time to collision is even closer than previously. And we have provided a XANDAR approach to consider timing from the early stages of the development until we actually deploy the software on the hardware. We've shown the process and shown that we can implement tools and use the tools, Prevision and the TA tool suite, to then identify the flaws and also address them. And this helps us to reduce stressful failure search and expensive testing in the end. And this also concludes the presentation. Thank you a lot for the attention, and I'm looking forward to any question that you might have.